All right, it's 8:05. I'm going to go on and start. I'm not going to bury you with slides today. I'm going to bury you instead with concepts. And I really want to go slow through the process because I will tell you, and I do not joke about this, I could probably continue to talk about regression. I could continue to talk about all the different methods that are out there now that we last week laid down the foundation of what statistical inference really is about and what a p-value is truly about, and how to really consider what you're doing with regard to your design. But I will be very honest. I think tied with a misconception of what the p-value is a complete misunderstanding of what statistical power is. And when do you need a power calculation? What is a power calculation? I will use a little bit of profanity in my description of what a power calculation is, so you will forgive me. And then we're going to talk about how we go about it and how I go about it when we go to submit grants. I will also talk to you briefly in the first piece. You should get out early today, but I will add a piece to talk to you about a thing that is very problematic to statisticians, and that's a concept that is often asked for by journal editors and usually journal editors when you go to submit a manuscript and you have reported your results. They will ask for a concept called observed power. It has no mathematical concept whatsoever. It's not a good question. Now, that doesn't mean you tell the editor that. That will not get you published. Trust me. You do not do that. But you must negotiate that one very, very carefully. Okay, so what are we going to do today? We're going to start out with getting to what the textbooks never do. We're just going to skip it, where I'm going to give you the overview of what statistical power really is. Okay, I'm going to give you why it's not the most important part of the power section is not the actual calculation. Okay, it's not the calculation. I have no stress whatsoever about writing a power calculation. People will come to me and say, "Are you certain it's right?" And I will make them very upset with me. And I'll go, "No, I'm certain it's wrong." And I'm okay with it. Because the very first word in every power calculation I write, you'll know I wrote it. The first word is assuming. Assuming. We as a team have to make assumptions to get a power calculation fleshed out. All it is a description, folks. It is a description of what is likely to occur if our assumptions are correct. It's not a guarantee, it's just a description. That's all it is. To treat it as anything other than that is actually doing it wrong. And as you can see, as David always does, he races ahead in his discussion and doesn't wait for his next slide. Bottom line, what is it? And I've bolded pieces. It's simply a description of the possible experimental outcomes for which we are likely to declare that the intervention and experiment worked. That's all. Okay, so let me ask you something. You come up with we decide we're going to, and it's intuition, folks. We decide that we can only afford 50 people. We're going to come up with a new diet. All right? Your new diet. Suppose your new diet makes people drop just 5 pounds on average. Okay? Well, there will be a power to that, right? We did have an impact. We made them lose weight. Okay. What if your new diet made them drop 25 pounds? Are the outcomes the same? No. Is your probability going to be the same of declaring, hey, I found it? No. So the bigger the effect, the bigger the power. But the hardest thing that goes on in research is defining what that effect is. What's clinically relevant? Okay? And when I design these, when I do power calculations, I try to take that off of you. Okay? I can't take it away from you. You've got to work with me. But instead of you feeling like, well, I've got to come up with the sole number that defines clinical relevance. Okay, that's a little tough, okay? That's putting you on the spot. So why don't we give me a range of, it could be between, I would start here, but what if it's bigger? Okay, let's find the smaller one, or maybe let's find one a little bit, do a calculation on something that's a little bit smaller than what you might define, and just study the landscape. The other thing is, people will come to me and say, David, I want a power calculation, or I want a sample size calculation. Okay. And they'll stop me on the street and say, I need a sample size calculation. And by the way, I can only afford 50. Okay. You mean you want an effect size calculation? That's what you mean. But it's important to recognize they're the same side of one coin. All right? They're the same concept. If you come to me and you say, I'm stuck and I can go no higher than this, then I'm obligated to describe, given we can get to 50, these are the effects that would have 80% power, okay, to be detected. It's one of two things. It's one really of three things. It's either a power calculation, where you say to me, I want this effect size and this sample size, and then I go get power and solve the equations that way. Or we can say we're going to fix power and fix effect size, and then I solve the set of equations back to what is your sample size that maps. Okay? Or we can go the other way and say, David, I need this power and I'm stuck here with this sample size. Give me the effect size. Those three things work together. Set two, solve for the third. That's always the game. If you can't do that, there's still a way for me to work the problem. All right, we just have to. But here's the thing. Do you see? I think the most important bolded thing on that screen is a meaningful effect. It's a clinically relevant effect. If you cannot come to me and say, David, I need you to design a study to find me something that's statistically significant, that is the tail wagging the dog. Okay, we cannot do that. I can do it. Understand, I can do it. But it's the wrong thing to do. Because you give me enough money, and you give me enough time, and you give me a big enough sample size that I can find very small things that are statistically significant and clinically irrelevant. Okay? You laugh at me. One of the things that we struggle with as statisticians is, the most powerful tool I have usually in my back pocket is regression. If I need to, that's my battleship typically when I am doing hypothesis testing. Because what that does for me is I can come in, you want to know if there's differences between groups? Well, I can add a covariate and increase the power. Because by adding the covariate, I start pulling out variance in your outcome. For example, if we're doing a study of blood pressure and we are going to compare two drugs, naturally, I'm going to throw gender and I'm going to throw age into the regression, because that will pull some variance out. And if I pull variance, if I decrease my variance, the statistical trick, decrease the variance, power goes up. Okay? But you got to be careful there. Because at that point, eventually, I can get to finding things that are so small they're irrelevant. I have had regressions where I've increased the R squared by a whopping 1%, and I get p-values less than 0.0001. All right? Can you really tell me that that's clinically relevant? I've explained 1% of all the variability in that outcome by your treatment. And so we've got to be careful. We've got to be able to define it. I'll help you with that. All right? Why statistical power is not the end-all, be-all. It is the reason I have a job, I'll be honest. It is the reason people keep me on the campus. I really believe that. But please understand, it is not the first thing to be worried about. At earliest, it is the third. Earliest is if you stop me on the street, and people do this, and I need to talk to you about sample size. Like, I don't have the formulas in my head. Okay, I can't do that style of math in my head. Okay, and yes, there are tables out there, but they're not very helpful. Okay, they really need to be customized. First thing, you're gonna get sick of this. Gene can tell you this. The first thing is the first thing. It's always the specific aims. There is no reason to even start conceptualizing statistical power or sample size until your aims are written down. And I'm not saying you can't modify them, but they have to be a very good draft. Very good draft. Why? Because your aims are where I find your hypotheses, right? And from your hypotheses, I understand the nature of your outcome. Is it continuous? Is it a blood pressure? Is it yes or no? Is it a dichotomous outcome? The person went into remission, yes or no? Is it a time to event? That the person stayed in remission for 9 months. Okay, is it a time variable? These things are critical to me because until I get aims, outcome, analysis plan, once I get to the analysis plan, now I can go and pick the correct power approach. You cannot disconnect those. Those 4 things pass information into each other in that order. You cannot pick your analysis plan and then retrofit your aims. Bad science. Bad approach. Always aims to outcomes, to analysis, to power. Okay? In the aims, I'll know, are you talking about a 1-group design, pre-post, 2-group design, more than 2 groups? All those things play into helping me map to the correct analysis. Just because I tell you you have 80% power, you know what that means? 4 out of every 5 experiments, if the assumptions are correct, will end with a p-value less than my type 1 error rate. That means 80%, which means 1 out of every 5, even though you have had an impact, your statistician's not going to be able to find it. It is not a guarantee of success. Okay? It is a probability statement. That's all it is. Under these situations, 8 out of 10 of these 8 out of 10 future experiments, if we did it 10 times, we would expect 8 of them to spot it, and we would expect 2 of them to miss it, even if it's there, when it is there. The other thing, it is not an exact measurement. It is a guess. In fact, this is where I swear. It's a swag. Do you know what a swag is? Anybody know what a swag is?
Free stuff at the conference.
What?
Free stuff at the conference.
Nope.
What did she say?
The free stuff at the conference when you walk through. Or it's the free stuff that they give you after you run a 5K. Right. No, that's not it. That's a good idea, though. Swag. Scientific wild ass guess. It's really what it is. Okay? I'm sorry, but that's what a power calculation is. And it is required, and it's a reasonable exercise. But it's a scientific guess. And sometimes, and one thing I'll show you, I did it last night at 12:30 a.m. this morning, actually, because somebody contacted me yesterday at 5 to submit a grant this afternoon at 5. Okay, I'll do it. I shouldn't do it, but I did it. And I wrote one paragraph. If I ever write a paragraph and that's all I give for a power calculation, you know it's a rush job. You got to know I've had to rush it. It's not good. It's not the way to do it. Not the way to do it. Because it's not an exact measurement, there should be multiple, there should be a grid of power or a power curve. I'm not a fan of the curves because it's kind of hard to interpret, but most people can interpret a 3x4 table. And I'll show you what I'm talking about. Okay? And this is when you're collaborating with a statistician. Notice I said I use the word collaborate, not consult. Please don't turn it into a consulting relationship. Collaboration is team science. It's where you bring your knowledge, I bring my knowledge. We work as a team to achieve a solution that neither one of us, independent of each other, could ever come close to. I need it to be a collaboration. How to approach the power calculation. I'm teaching you, okay? When you have your specific aims, you find a methodologist to sit down with. Now, am I usually in the rooms? Have I been in the room where I've been drafting the specific aims with my collaborators? Absolutely. I've been there. But we are not going to even imagine discussing power until we've got those things laid down. Don't start anywhere else. Always think, when you're going to talk to a methodologist, is it a continuous outcome? Is it blood pressure? Okay? Is it blood pressure? Is it weight? Is it height? Here's a hint. People say, well, how do I know if it's continuous? Does it have units? Do you have units on it? It's continuous. If we throw units on it, then we can talk about it being continuous. Okay? Is it less than continuous? Is it yes, no? Or is it ranks? Is it, agree? And I get data all the time like this. Agree? Or strongly agree, neutral, disagree, strongly disagree. That's a different method, but I know once I see that, I know where I can play in my statistical theory, where I've been trained. I know where I can go to get the correct analysis that will meet those assumptions.
Excuse me. A percentage is a continuous data?
Pardon me?
A percentage?
A percentage I can treat and transform onto a continuous scale. But yes, you can do, there is such a thing called the uniform continuous distribution, and you can trap it from 0 to 1. Okay, so yes, I can do that. There are those distributions. If you're studying percentages and you want to do like a regression style, there are some transformations I have to employ to make the assumptions of regression hold. But all of that, again, that is way down the street. What we do is we just start with, David, I need to measure this as a percentage. Thank you for telling me that. We'll be going down this road, we'll get to this power calculation. But yes, percentages can be considered continuous. Okay? Then we got to go, and this is where people get nervous with me. Think about what observed changes association would convince you that the research hypothesis is true. Which one's the research hypothesis again? From last week, let's measure your retention. The alternative is always your research hypothesis. Immediately after considering these things, once you've got it down, then we can get into stats methods, which is what everybody wants to do, right? No. Okay? All right, so here we go. This is the way we actually go through a power calculation, okay? Remember there are two hypotheses that come from, first remember there are two hypotheses that would come from your specific aims. There's always the research hypothesis is the one that we seek the evidence in favor of. The catch here, when I do a two-group hypothesis test, what I'm really asking is, I'm going to randomize, let's say we're going to do a randomized controlled clinical trial. Why do I randomize? Because that makes everything balance out, and there's only one thing that should be different between the people. That's what drug they got. Everything else has to be broken up and not associated directly with their treatment. So I can get a direct test. But I'm asking, are there two probability distributions? Notice what I've started doing here. I added something this week. Now you see the null where I say mu1 is equal to mu2. I'm playing with BMIs, and I'm just going to talk about, we'll look at the post-BMI, okay? Perhaps we could say mu1 is, if I assumed mu1 is 30 and mu2 is 30, guess what? The null is true. You've just made an assumption that puts you into the situation where the null is true. There are other possibilities. You could have assumed mu1 is 25 and mu2 is 25. There's plenty of ways to do that. But once you've done that, once you've set it, you can move to the alternative, in any other pair that does not give you equality is technically under the alternative. Now here's the game I want you to play with me, okay? 30, 27.5. Clearly that's under the alternative, right? 30 and 25. Clearly under the alternative, right? Great. 30, mu1 is 30, mu2 is 29.9999999. Which one's true? The alternative. There are several conditions that you could work with regard to the alternative to try to find power. Trust me, if we're going for 29.99999, I'm pretty certain you're using a type 1 error rate of 0.05, I'm willing to bet your power is 0.051. It's not much, okay? Power never falls to zero, folks. Also keep that in mind. Most people make that mistake. Power does not fall to zero. Power can only fall to your alpha rate.
To what?
Your alpha, your type 1 error rate, 0.0. So if you're using 0.05, your min power is 0.05. All right? So just keep that in mind as we play this game, okay? Because if I bring these things closer together, it's going to get much harder for me to spot it. Okay, the further apart I take them, the easier it is for me to spot it. Okay? All right, so here's the review. We kind of started playing this game last week. This is the upper panel, is what's going on with the null. Okay? Now I'm going back to what I tried to talk to you about, Neyman Pearson, right? The reason people can't understand power is they try to associate p-value and power. They came from two different camps. They came from warring camps. Fisher was worried about p-values. Neyman Pearson, they were worried about type 1 error rates and power. Now we've rewritten all our textbooks, smashed everything together, and nothing makes sense anymore because we hid that fact. If you will not think about p-value, it's the last thing you should ever do when you are conceptualizing power is to think about p-value. Just step back and say, I'm going to go old school and work with rejection regions. Okay? Naaman Pearson said, draw the curve and draw rejection regions. Show where you would reject under the null. Well, that's what the upper panel shows. If you go above the green line, which is running slightly above, and you can slightly off, and I didn't do a good job dropping the verticals. It's slightly below 2, the other one's slightly also below -2. If you could take a little bitty marker and start shading the little bitty tails, I'm trying my best for everybody that's online, you could shade the upper tail and the lower tail in the top graph, that's 0.05. 5% of the area is caught there, okay? That's how I've defined my type 1 error rate. Most of my power calculations, except for genetic studies, are using 0.05 or 0.01, okay? Well, then we make the assumption. We just start playing the game, okay? What is my alternative? Well, if I put it at 2.5, if I put the gap, if I put the effect size as 2.5. David, what do you mean the effect size 2.5? 30 minus 27.5. It's the difference between the means. I should divide by the standard deviation, but I built this problem, so I made the standard deviation 1. Okay? What that does is it literally takes the distribution and shoves it over toward the right. Okay, one moment, it shoves it. And now your power becomes on the bottom graph, how much of the area of that curve is above or below one of the rejection regions. So we would have to take, if we had the ability to shade, I'm going to get Brian to get me a new screen where I can actually draw on it. I would shade all the area above 2. Now, technically, because it is a real distribution, this curve keeps going down below -2, and there's an itty bitty probability down there, probably about 0.001, but you got to capture your calculations off just by a hair. Okay, we got one question in the far back, then we've got your question. Yes, ma'am.
At what point the power should be considering, or the p-value should be considering the one-tailed?
That is a great question. So, to repeat the question for everybody that is online, David, you are assuming a two-tailed test. I can technically increase my power, which is a true statement, if I chose to go one-tailed. When do you choose to go one-tailed? David never goes one-tailed. David never goes. I've never successfully gotten it through study section. I find it problematic to go one-tailed because, let's be honest with each other, if your study actually comes up completely paradoxical to what you believed it should be and it's statistically significant, are you going to put it in the drawer? You're not going to report that? You're not going to try to publish that? We're all going to try to publish that. So I've always set it up as two-tailed. Though I anticipate diets causing people to lose weight, that is what I hope, I do put part of my alpha on the other tail.
But non-inferiority test, isn't it typically non-inferiority studies?
A non-inferiority study is a very, very unique case where we come in and we actually try to demonstrate that two treatments are so close together that they have fallen within a boundary. A non-inferiority is a one-tailed test, but an equivalent study is a two-tailed test. Okay? So there are special cases, but in general, I avoid going one-tailed unless it just makes perfect sense. Okay, because usually study section criticizes you for making that assumption. The other question.
How did choosing an effect size of 2.5 affect that second graph? Did it affect where it fell?
It affects where its center is. It moved its center up. The center is under the null, 0. This one brought it up but it doesn't bring it all the way up in the sense because I am still having to adjust for sample size and all of those things.
But how did the actual number, because the x-axis is like the standard deviations,
Mm-hmm.
right? So the effect size of 2.5, how did that, like if we had chosen an effect size of 2 or 3.
All right, we're going to play that game in just a minute. That's where I'm going. That's what I want you to imagine. That's why I want you to always, when you're meeting with a statistician, imagine these two curves. Because I'll go on and start playing that experiment with you. Suppose I had chosen 1. I shove back this way. Because if it's a smaller effect size, I move it back toward my 0 effect. What's happening to the area as I shove it back toward 0? I get less in the upper tail. Power went down. Suppose I keep pushing it out into the further and further out. What's going to happen? Power approaches what? 1, because you'll have the whole curve above 2. That's what a power calculation is. That's all it is us making judgments, and then we've made one set under the null, we've made another set of assumptions under the alternative universe, and then we did the calculation under the alternative universe of how much of the area is above the rejection region. That's it. Congratulations. Now you understand more about power than 99% of the population of the United States. And almost all the people on this campus. I promise you that.
And is the power just the area under the curve that's outside of your rejection?
That's exactly it. That's all power is. That's all it is. I'm sorry, it's nothing more and it's nothing less. Okay? So let's go to the next slide. Okay? So let's play this game. Let's assume that the common standard deviation is 5. I've got to know the standard deviation. Okay? You're going to say, but David, I don't really know the standard deviation. That's okay. Not my first rodeo. We can work this out. Assume that we wish to use a type 1 error rate of 0.05. Okay? I know it's not carved in stone. Finally, assume that the researcher believes that most of the budget can afford 30 per group. Okay? I'm realistic. Usually when I come in for a power calculation, the first question is halfway down, once we got the aims, once we've got the outcomes, I just look up and say, how many can you afford? Okay? If some people say, no, and there are times that we go for budgets that are quite big and we have the ability to move the sample size around, but sometimes it's just, David, we can't get above this. We can't get that above that population. All right, we can do that. Now, be careful, okay? See this? Don't steal it. It will make me cry, okay? There is a software on here that's $10,000. Software. Perpetual license. Okay? Department bought it. The biostats department bought it. I've got it for the rest of my career. It will be updated every time it needs to be updated. Free. Except for that 10 grand charge. You know what that is? It's called Pass 14.0. It has every different power scenario that I need to be able to program. And I can come in and build it. My preference that the FDA will accept. That web page, unlikely the FDA is really going to accept it. Okay? Be careful. I'm giving you that as you can go and experiment. When you get ready to submit grants or submit papers, please have somebody verify the calculation. I'm not saying you can't do the calculation. I'm not saying you can't do it right. I know plenty of people I've taught to do these things correctly. But it's always good to have two eyes, two sets of eyes on there. Okay? So we enter the information. The difference between the means, 2.5, common sigma equal 5, alpha is equal to 0.05. Tell the software you get 2 groups of 30. One moment, the software will get you power. And it comes back and says 0.4779. If you get a power calculator, and if you're ever on a web page and they tell you the power is 1.1, what do? Stop using the web page. Probability, what is power? It's the probability of a future event. Probabilities do not go above 1. Probabilities have to stay between 0 and 1 unless they're power calculations. And then they have to stay between your type 1 error rate and 1. Okay? So under those conditions, you would only have a 48% chance. Coin flip. It's a coin flip. Okay? That good?
No.
Nah. Okay. And I'm also going to tell you what I've learned over my career. All right? But here's the thing. Tell you the other reason I wrote that paragraph for that person last night. Okay? I could have thrown the information back to him. No, I wrote the paragraph. Because at the end of the day, all journals are pretty much requiring a statistical editor now. A lot of the faculty in the biostats department is actually starting to get % efforts to say, the journal says, will you commit for a year to be a statistical editor? So that we are checking to make certain that things are being done right. Are the power calculations correct? Or can they be replicated? That's a better thing. They're not correct. Can they be replicated? The one reason I say, let me write the power calculation, not you. It's not because I'm arrogant, but I am arrogant. That's not the justification for that. Is because I know not to leave out the key details. Jean's been in hundreds of panels with me, and she's heard me say it. Whoever wrote the power calculation has not provided enough information for somebody else to reproduce it. People are going to always come in and say, can I turn on a computer and reproduce that number? Assuming a two-tailed hypothesis and type 1 error rate, you've got to put in there what is the assumed type 1 error rate and a common standard deviation of 5. I've got to have those two pieces to be able to do the calculation. You leave it out and you say I have 80% power to detect a difference of 2.5 units, you're out of study section because it can't be reproduced. I don't know the standard deviation. I don't know the type 1 error rate. Then a total sample size of 60 provides 47.79% power to detect the difference between two group means of 30 and 27.5. Everything's there. Effect size, type 1 error rate, standard deviation, okay, sample size and power, okay, all those have to be stated. And then I start out with just telling them what I assume. Now, you can come back with, David, what happens if the standard deviation is 6? Is this still right? Hey, it's never right. And yes, I need to update it. Okay? It's never right. So, what if I wanted to play the game? I can play this game. Moving the means increases the power. I pulled them further apart. I actually told the calculator, all right, stop. You tell me, calculator, how far do I move the means apart to get to 80% power under these assumptions? It did. Assuming a two-tailed hypothesis, using a type 1 error rate of 0.05 and a common, same sentence, 60, but I wanted 80% power to get 80% power. Remember, the first one was 47, and that was 2.5. To get to 80%, I'm going to have to move them further apart. So to get to 80%, I had better be looking for about a 3.3 difference. Okay, that would give me 80% power. Now, is that clinically relevant? I don't know, Margot. You tell me. I'm not the clinician. I don't know. But the whole point is that we would sit and talk about it. We would discuss these things. What is clinically relevant? Okay. The other thing, coming in. Well, suppose you, David. No, I'm adamant, David. I want 2.5. Okay, the other lever I can pull, force the sample size up. This is also a true statement. I just gave you 3 power calculations that are all correct calculations. Are they correct? I don't know. I'm making assumptions, but I can reproduce them all. Assuming a two-tailed hypothesis, now we say, all right, if we've got to have 2.5 as our clinically relevant, you're not getting by with 30 and 30. You're getting by with 64 and 64. That's the sample size I would need to get 2.5 and 80% power, assuming a standard deviation of 5 and a type 1 error rate of 0.05, two-tailed. Okay? Hold those types of power calculations, this type here, this paragraph, because that's what you should. There will be a paragraph like this somewhere in your grant. It needs to have those types of details, or there should be those type in your paper. Okay, in your papers, you should have something very similar to that. We got to get going. Proportions, changing the game. When the outcome is dichotomous, proportions are typically the outcomes. Yes, no, I end up doing. Now, please understand something. People come to me and go, okay, it's so much easier. I got the continuous. I want to dichotomize it. No, you don't. No. Sample size on categorical outcomes, much higher, always. Always than you giving me a continuous outcome. You can give me a dichotomous when it makes perfect sense. But if you can, get me to a continuous level. It's easier on the statistician, it's easier on you. You don't have to pull a standard deviation. All you got to do is give me the proportion. David, I want to know, I expect 50% to respond here, 70% in the other group. That's it. That's all I need for the calculation. That's just by raw statistical theory. Go back to your binomial distribution. If anybody taught you a binomial distribution, you got to remember that the variance is a function of the proportion. So once you hand me the proportion, you accidentally handed me the variance of that proportion also. Okay? So just giving me the proportion is all I need, but it's the exact same game. But notice the shocking difference here. Again, I play the same game. 0.2, that's the null. I can imagine all the different scenarios I might want under the alternative. But this one I chose 0.2 versus 0.3. Margo, 0.20 to 0.21. Bad or good? Bad. They're really close together. It's going to cause a massive sample size. 0.2 to 0.4? Better, because it's going to, bigger differences would require smaller sample size to detect the same power. But notice this. You say, wow, but the total sample size here is already at almost 600 people just to spot that difference. Doesn't really matter. It doesn't matter what the outcome is. It does not matter whether this is response or remission or turning people blue. 0.2 and 0.3, that's all that matters to a statistician. Okay? So if you're looking for those proportions, it doesn't matter what the dichotomous outcome is, it's going to be nearly 600 people. This is what you should expect. This is what you should demand from your methodologist. Yes, I just said you should make demands upon me and all of my colleagues. Do not let us be lazy. Make us go the extra mile for the good of science. This is really what I prefer to put into a grant. And if I'm writing a letter back to the editors, I will include this. I can't get this into a manuscript here, okay? But this is nice because did I not tell you that these things are assumptions? 2.5, 3.5, 4.5, these are the effect sizes that I'm assuming. What I'm doing here is I'm showing you I'm not certain. You're not certain. Why are we pretending that we're certain? So let's do the range of calculations. Let's do the calculation where I assume the difference is 2.5 and the common standard deviation is also 2.5. Well, that combination gives me 97% power. As I increase, Margot, as I increase my effect size, what happens? Power always goes up. Oh, look, that makes rational sense. That makes reviewers feel good. They understand. Oh, look, what happens when I increase my variance? What's happening? Power goes down because it's noisier. That also makes sense. But people could come in here and say, okay, under this scenario, that's kind of marginal, but it's still above 75. But generally, if I'm hoping for something as small as 2.5, I've got to have a tight variance or tight standard deviation. If I get into larger effect sizes, I can survive a variance all the way up, or a standard deviation all the way up to 5. And then we come back and we say, from literature, we found the following range of standard deviations. Therefore, we believe that we are appropriately powered for the following scenarios. Not the scenario, the scenarios, because this shows the landscape. Okay? And if I was, like I said, when I write my analysis section, I would come in and decide, I would use covariance to try to force the residual standard deviation down into the range of 5 so that we would be adequately powered to detect things as high as 3.5 or bigger. Okay? It's not the calculation. The calculation is not the key thing. The calculation is never the key thing. It's the write-up of the calculation. If you, folks, you don't know how many times I've gotten grants at study section where we have 80% power to detect a meaningful difference. What? What? That's not even, you didn't even do a calculation. I don't believe anybody did a calculation. If you had done a calculation, you would have provided more details than that. You know what that is? That's a 7 and not discussed in study section. Okay? If any detail is left out of the write-up, then your power calculation will be questioned. That's true also for manuscripts. So have a methodologist inspect it. Even if you do even if you try to build the table first yourself, which I'm very confident you can do it. Most of the software is intuitive. Still, have somebody inspect it. Have somebody verify it. Have somebody look to make certain that all the details are in the write-up before it goes in. Okay, now let's talk about that nasty thing, and then I will give you a 10-minute break to have coffee and more sweets and more fruit and whatever else is out there. This nasty thing that people will say about observed power, or that they ask for observed power. So this comes up, and I need to, this will be a discussion, okay? If you've got questions, ask as we go through it. The problem with observed power is this. What they're asking the statistician to do, or they're asking you to do, is you failed to reject the null, okay? You didn't achieve statistical significance, so you've got a p-value somewhere above 0.05. And a lot of times, because of that, the knee-jerk reaction is, well, what was your observed power? Okay, wow. What they're asking you to do is to say, based on the effect size observed in your data, okay, not what you deem clinically relevant, but based upon what you realized in the experiment, what is the probability of rejecting that effect size in a future trial? Okay, now here's the problem. This is what statisticians don't like. A, you're now allowing your data to define clinical relevance. Okay, you can't do that. The data itself should not define the clinical relevance. And the other thing is, there's no such thing as observed power. The very phrase is an oxymoron. Okay? Margot, what's the probability that I am going to be the father of 3 daughters? What? I have 3 daughters. I have 3 daughters. That's the probability. Margot, what's the probability it's going to rain yesterday? 1. Margot, what's the probability it rained last Saturday? It didn't. Not in Birmingham, at least. Okay. Past events, such as your experiment that has already concluded, cannot have probability. Probability is talking about something in the future. To say you have observed power, you've observed it. It's got to be 0 or 1. It's 0 or 1. I typically will turn around and say, and I'll make it very clear to the editor what I have done. You have asked for this. You have asked for me to calculate observed power. And I will say, based upon the variances we observed in this trial, a future trial would need this number of individuals to detect a significant, a clinically relevant difference. I keep the clinical relevance with the PI and then say, I will use the variance from our experiment, because the variance is something I need to estimate to get the job done. It's not the main thing under investigation. Does that make sense? I mean, to ask about power after the experiment is over is wrong. It just does not make conceptual sense. That's why statisticians don't want to do it.
So I have a question.
Sure.
When someone asks about observed power, I wonder if one was wondering about, now you assumed many things when you calculate power before your experiment. For example, you assume the effect size that you don't know. You assume the
standard deviation, which you don't know.
You didn't know at the time. So when you are done with the experiment, now you have the actual possible effect size and the standard deviation from your data.
Right.
So that kind of makes you able to see what power you were dealing with.
No, you just stepped over the line. You were doing great up till that last statement. You were doing so good. I was about to say, I agree, and then you stepped over the line, and I'm sorry. So you have, and I've done this many times, and I've done this as a way to successfully discuss with editors. I will say that, if you have the power calculation from before you ever began the experiment, that's the one that goes in the article, okay? And then when you get a null result, if you do, unfortunately, get a null result, in your discussion, you can say, we assumed we would be able to detect a difference of this magnitude. Our data provided this estimate. Clearly, our estimate is much smaller. You could say our estimate, what we observed, is smaller than what we observed. Perfect. That's good. You're not talking about probability. You're talking about what you observed.
You can't talk about the probability at that point.
Can't put a probability back on it. Then you can come in and say, or you could be in the very fortunate scenario of, and I would argue the best scenario under a null result is to be able to say, we did produce a difference of that magnitude. However, our variance or our standard deviation was higher than anticipated. You're describing past events, but resist the pressure to put a probability to it. Okay? If you want to talk about probability, you've got to come back and say, in a future experiment, then. Got it? That makes sense?
Yes, makes sense.
Okay. Didn't mean to be harsh, just didn't have enough coffee this morning. Yes, ma'am.
Is there a value for what he was talking about? Like, once you do the experiment and you want to, I don't know,
All right.
say this is what we got, like, I think observed power is obviously not the right way to quantify what they're going for, but is there something that would be a replacement for that?
I think what he was going for is exactly what I would recommend, is a detailed discussion
Of the variance.
of this is what we assumed, this is what we observed.
Mm-hmm.
How well do they agree, and could that possibly explain why we rejected or failed to reject? The irony is, I've even had people come and say, well, what's your observed power when I declared everything to be statistically significant? I'm like, what? What do you mean my observed power? My observed power is 1. I did reject. So I've rejected. It's got to be 1. But it's just a confusion of the idea. It's the same idea of, and just remember, what's the probability that David's going to have $3? 1. It's already been observed.
But I think the question or the question is, when you get a null result.
Why do I have a null result?
Right. So then when you go back and you start, as a clinician or the investigators, we start to wonder if we have more patience for the.
So
that's
the first thing to do is to get off the don't go back to probability. Go back to what, I mean, the answer was perfect until the last sentence. I would still give you an A. First, go and talk about the observed effect size. How big of a difference was it? And just be blunt honest about it. Was it of the magnitude you thought it would be? The answer is, if it's no, then say no. And declare that we did not achieve what we believe is a clinically relevant effect here. Okay? Not every one of your experiments is the alternative going to be true, folks. Sometimes you're going to design an experiment, and that's not bad. If we would make a lot more advance in science if we would publish null studies. Because instead of you coming up with the same bad idea as somebody did 5 years ago, you would already find it in literature, and well, we're not going to go there. Or we're going to improve upon that. But you're exactly, going back to what you're saying, it's what I would do. If I have a null result, compare what I observed to what I assumed. Look at all of them. The difference, the effect size, the variance, those types of things. If it's the variance that's blowing you up, then what that's telling you is what you do probably have an underpowered trial. Okay? And you could say, if we were going to do this again, we know we should have gone to this magnitude. But it's a matter of not going into probabilities. It's a matter of talking about what was observed. Okay? All right, guys, y'all take let's go with a 10-minute break. Well, we go to the literature, or we get a pilot study.
Okay.
Give me 10 people, and you give me a standard. I'll give you the standard deviation.
Okay. So it's mostly from the literature.
From the literature or from your previous. Hello, Dr. Dean.
How are you?
Fine.
Okay, I have a
You
question.
should become a dean. That would be great. Dean.
I've already did movement disorders, so that's 3. It's my first semester, so it's a dean, MD.
Oh, cool. That's cool.
Well, I already. Okay, so when you're talking about power, you're assuming that both the sample sizes are the same. So in what situation like would you want your sample sizes to be different?
Rarely.
2 to 1 or 3 to 1.
All right, when we're doing that is you've got a belief for some reason that one drug may be more toxic than the other, and you want to avoid that, or you want to be able to provide a more precise estimate on one side of one treatment. But the problem with that is that's always going to cost you money. If you can do 1-to-1, or if you think one group's going to have more variance than the other, because the other thing I'm assuming is the variance is the same. If you know one has a much more noisier situation, you ramp up the sample size on that side.
So how does that with the calculation you're doing it with the total sample, right?
Yeah, but you see, you would say, David, I want 2-to-1, and I can come in if I fire up. It's right there. Allocate 2-to-1, so it adjusts the calculation. All right. You don't eat enough. I will never see you. I'm fine. How are you? Are you all right? Talk to me. Don't just talk to me. I know you're good. It's only problem. Who are these people? I may be killing some people too. Me. And you. We're rational. We're lovely people.
You know, sometimes people are homeless because of mental illness and they're wandering the streets. Research subject, teaching, polar, people wasn't making that stuff up. People were disappearing. Yeah, they do get a you know, rolling is big. Rolling
It has been a very rough spring.
I'm like, yeah, my girlfriend said that she's a social worker at Morgan. She's originally from New York. And she's like, that's why I can't but she
Tracy, you gotta be here.
that's what we said. I said, how did we keep it? We had this conversation. She's like, they're trying to get black people.
She's doing fine. Oh yeah, she's back in soccer. She's back in soccer and doing great. Just doing regular. Yeah. Crazy. Well, you see, the catch there is for us is our middle one is travel softball, and so just too many. So we already divide up. Sam goes one way, I go the other. And it just gets old. In fact, I'll be very honest, there was one weekend, 2 weekends ago, that Sam and I barely saw each other. We had one at softball and one at soccer.
So it gives us some credibility going you better get the name my phone for my dissertation, I recruited 125 people in less than 60 minutes. My phone was ringing off the hook at 6 o'clock in the morning when I was in the Stairmaster. I had a toll-free number 1855 something sugar. So they were calling me, something else, is this call free? Because you know they have all people's phone. I said, yes, ma'am, because I was recruited on 6500. They said, okay, then they started just talking. I'm not being in a study. I said, okay, let me see what I was all over Jefferson County and Tuscaloosa Green and Hale. They gave me an office in one of the senior centers. And when I would get there, it would already be lined up so I could get waiting to participate. You know what I did to get back? I borrowed, I did a graduation. I had a cake made with a cap and gown on it. Right? My dissertation chair let me borrow her cap and gown because I haven't even had my cap and gown yet. Right? And we found prompts and circumstances on the iPad, and then all the seniors came, and then I walked and they stood up, and they were clapping and everything. It was great. And they took photos with me in the camera and everything. And they were like, all right. And then they were like, the ones that didn't participate, they said, I'm sorry I didn't participate, can I still take a photo with you? Okay, absolutely. I said, I understand this one here. I see how open you're doing somebody else.
Okay, so let's pick back up. And then I'm going to try to be really efficient here. The talks were actually designed to go over 2 separate weeks. But what I'm going to do here is, and that's why I'm kind of going right back to the slide, it's the idea again. And what I want to emphasize to all of you, if you can keep in mind, David is always in his head when he's doing power imagining two curves. He's imagining two sets of curves, and he's drawing lines in his mind and saying how much of the curves fall above the line. Under the null, it's got to be constrained to be my type 1 error rate. Under the alternative, as I move that distribution left and right, I'm causing numbers to move up above 0.05, closer to 1. Okay, that's the way it works, but it's always the same game. No matter what hypothesis test, all right, first, I would love to tell you I'm a nice guy, but Mama told me it's not good to lie. So I got into an argument in this room a few weeks ago that with someone who said, well, we put this p-value down. To which I said, okay, you put a p-value down. What was the power of where's the design? Tell me, where's the a priori power calculation? What was the effect size you were looking for? What assumptions did you make before the experiment? To which the person said, we don't do that in this field. To which I responded, then don't use a p-value. Because technically, it is, even though they came from different branches, sorry about that. I was like, that's my phone. If it has a p-value to it, it implies that there was a hypothesis test. And if there's a hypothesis test, there is a way to get to power. Just that easy. Okay? Though when you're doing the calculation, you need to push the p-value aside. If you put a p-value down into a manuscript, somebody has a right to ask you, did you consider power? It's a fair statement. Okay? But what I want you to recognize is this. If you can keep the ideas of the graphs in your head, you never have to worry about what's your design. You understand the fundamentals of power. Because here we go to the more complex situations. Analysis of variance. Okay, ANOVA, as it is called. Analysis of variance. What does analysis of variance test? Differences in means. It's a trap question. Okay? It's an analysis of variance, okay, though you are testing means. Okay? Analysis of variance will always be used when there are two or more groups and you are studying continuous outcomes. Okay, if we can get the normality assumption in there, we're at ANOVA. Okay, if we can't get the normality assumption in there, we can back up and do other things, but generally we start looking at ANOVA to begin with. Let me ask you this, trap question. It's really not a trap question. If mu1 equal to mu2 is equal to mu3, if all those numbers are equal, do those numbers have variance? No. There's no variance. That's the variance you're trying to analyze, the variance of the means, if they exist. If they are all equal, that variance is 0. Okay? For the alternative to be true, you better move one of them. That way you've created what? Variance among the means. Okay, that's the concept of analysis of variance. But it's no different than the game we were playing before. Okay? We just talked to that. Let's skip over that, can contribute to the variance of the data. It's the same game as before, okay, but it gets a little bit more complicated. It's just a more complicated design. There are more assumptions, but it's the exact same game. You've got a null and you've got an alternative, okay? And so now, instead of assuming 2 means, you assume 3 means. Under the null, the 3 means must be the same. For the null to be true, they're all going to be equal. Under the alternative, you can pick any pattern you want. Okay, 30, 25, 20. That's valid under the alternative. I would be able to calculate power because there's a variance there. I could do 30, 30, 20. I can do that. Okay, I could do 20, 30, 25. It's no different. Okay, did you hear me? I just called off the same numbers. I just put them in a different order. It's going to generate the same variance. So you're going to think to yourself, oh, there's all these different companies. There's not that many. Some of them map to the exact same power calculation. Okay? But again, the combinations is just one of an infinite number you could pick. I'm not going to ask you to come up with the infinite number. We're just going to find a small subset and describe likely outcomes for a fixed sample size. That's all we're going to do. That's all it is. It's a probability calculation. Okay, and guess what? All we have to do is come in and start working out these different possibilities. That's all I want you to do. That's when you go to meet with a statistician, you've got to be able to say, because it's these things here that are giving me the effect size. It's not as easy as calculating just the difference between 2 numbers now. I've got to use other methods, such as a variance calculation, to absorb it. But nevertheless, it's just your idea. This one here is saying, well, 2 drugs create the exact same effect, whereas the 3rd drug creates a bigger effect. That's all. But guess what? Let's see if I can get to it. It goes back to showing graphs. The difference being is no longer a bell curve. Okay? When I go to ANOVA, I start studying another distribution. But guess what? I have a distribution under the null, and I have a distribution under the alternative, and I spent 5 years studying stats theory, so I know how those distributions will behave under different assumptions. That's all. So guess what? The red one is the null. Okay? Guess what? I dropped a vertical blue line here to define rejection region. Analysis of variance. Okay? Now think a minute. Variances are what? Variances are guaranteed to be, can they go negative? No. They're squared terms. Variances, if you look at every variance calculation out there, you'll see the square in the calculation. That means all the evidence is thrown up into the upper tail. Every negative value gets squared. So all of a sudden it becomes positive, and then it's summed. So all evidence gets thrown to the upper tail. So even though this is a 2-tailed test, all the evidence, by the way the test is designed, is forced into the upper tail. How much area do you think is above 3.8? That's 3.8. No, that's not 3.84. Whatever that value is right there. How much area do you think is below that red line? What? It's the null. What?
It's very little.
It's very little, but what is it?
5%.
5%. Exactly. Under the null, the vertical is always going to capture the type 1 error rate. Okay? So, where's my power? My power is always what? Under the alternative distribution, it's the area above the vertical line that is associated with the green. Now, here's the interesting thing. Now, this is getting a little bit further down into stats theory than you really want to do. This is called, the red line is called a central F distribution. The alternative is a non-central F. Now, as you play with assumptions, the reason that I like these graphs is not only do the changing the assumptions kind of shove things to the right to increase your power, it can actually warp and bend the green line. That's why you pay attention to the sample, the working of the sample size and the positioning of the means, not only shift it, but bend it in different shapes. Okay? Again, that's getting into it, but the take-home message is just always imagine a red line or a null distribution and an alternative distribution. And when you're doing a power calculation, all you're doing is measuring how much of an area fell above a given cut point. Okay, yes?
And the x-axis is not the standard deviation?
No, not anymore. That's the F distribution. Those are F values. Okay? It's the ratio of two variances. That's what the F is. And F is technically the ratio of two variances divided by their degrees of freedom. Okay? You should think about, honestly, a good way to think about what's on the x-axis is that those are that's the value of your test statistic. Very much. That would be the test statistic that you would be looking at. If we calculated out an F, for an ANOVA, you're going to get an F statistic. If I get an F statistic above 3.1 here, under the null, that's got 5%. Under the alternative, that would be my power. That's all I'm trying to say. That's helping you understand where your test, that's the distribution. Going through what we've done before. Assume the common standard deviation is 15. You've got, for ANOVA, you've got to assume every group has the same standard deviation. If you violate that assumption, you cannot use ANOVA. So that's got to be stated in your calculation. Common standard deviation, type 1 error rate. Again, assume the researcher believes that at most the budget can afford 30 per group. Okay, well then it's the same thing. And I go in, and this time it's a more complicated calculation, but again, I try to give every piece of information that would allow someone to replicate what I've done. Tell them up front, in a one-way ANOVA, sample size of 30 per group for 3 groups, total sample size of 90, just in case they haven't had their coffee in the morning and are reviewing very late at night or very quickly. Yes, I'm talking about 90. It'll only get you 62% power to detect differences among hypothesized means, and then I actually give them. If I submit this to like NIH, I put them down. Otherwise, nobody can replicate this. And it needs to be replicated using an F test, and there's my alpha. The size of variation in the means is represented by their standard deviation, which is 4.08. If you calculated the variance among those 3 numbers, you come up with 4.08. And then I tell them the common standard deviation with a group is assumed to be 15. If I give them all that information, they can get back to 61.6. Otherwise, they're not going to get there. My biggest fear is getting a comment from study section that states we could not replicate what the statistician stated. That's a bad thing. Okay? Again, avoid trying just to put one calculation in. Go in and show what's going on. Now, I've changed the game here. Okay, I've changed the game. I've done the assumed common standard deviation across the top, and then I just hypothesized the different means. Okay? Now, study the table and question me. Be my clinicians. Don't believe that I'm always right. Do you see something in that table that makes you go, huh? I'll be generous, 15 seconds.
The last 2 lines are the same.
The last 2 signs are the same.
Whole line.
Yeah?
How can
Yeah, but it's the same.
the numbers,
What about the numbers?
the percentages,
Their powers.
Yeah, because now if you're saying mu1 equals 30, I mean for the null, right? And you come up at 61.6, and then when you, I don't know, but it's just.
Yeah, I see where you're going.
The percentage is just, something is wrong.
Nope, it's right.
Yeah, the last two lines are the same because you're comparing difference, not absolute numbers, right? So difference between 25 and 30.
It doesn't
Same. Doesn't matter because you're just comparing the difference of the one group to the other.
All right, well, so let's be friends. How many of you think I'm wrong? I won't take it personally. I won't take it as a personal challenge. Okay, here's what's going on. Again, I want you to understand how to work with a statistician and a methodologist. When you see this, just don't be afraid to ask questions. It's team science. All right, first thing, Margot, as I go across, standard deviation goes down. If standard deviations go down, what should happen to power?
It should go up.
And they are going up. 61.6, 93.6, 99. Across all the rows, they go up as expected. Okay, so that makes sense. Okay, what this is, the 93.6 on the sigma equal to 10 in the very first row, that's telling me under those assumptions, for a fixed sample size of 90, I would have approximately 94% power. That's pretty high. That's pretty good, actually. I'm really surprised at this point nobody has said, Dave, what's a reasonable power? Where do you advise your clinicians to get to? We'll answer that before we adjourn. This is not wrong, even though these numbers differ, they have the same amount of variance. Remember, analysis of variance compares the variability of the means to the other variance that's in the background. Because these two map, these are the exact same effect size. And this is something the vast majority of people do not understand. Once the effect size, if two things map to the exact same effect size, they can't produce different powers. If it maps to an effect size, it doesn't matter what combination gets you to that effect size. Once you're at that effect size, the powers are going to be identical. I suspect Brian's recording me, and I'm going to regret being recorded on this. I have one investigator who will ask me, well, I've got this fixed sample size, and I'm going to do the 4 outcomes. I need 4 power tables. No, you don't. Your sample size is fixed. For all the outcomes, all the effect sizes are going to map to the exact same powers. I'm literally, I'm being recorded. I can't convince him otherwise. So I produce 4 tables that if I handed them to you, you would take a calculator and go, dear God, they're the same numbers. Yes, they're the same numbers. But I can't convince. So don't just always be able to ask the questions. Okay? Now, down here, we're not in good enough shape. I mean, if we're really thinking the residual standard deviation is 15, I'm going to have to come back to you and say, you've got to come up with a different set. Create a larger effect. If you cannot believe you're going to create a larger effect, you've got to come back and let me have more people. It's one or the other. Make a choice. We'll work it out, or do both. Adjust this a little bit, adjust that a little bit. Do not tamper with alpha, that's cheating. I've seen that at study section. Don't. I've had alphas come in at 0.2, and I'm like, what? You're going to take a 20% chance of making a false discovery? I don't think so. Here, in this scenario, you're pretty much overpowered. You're almost guaranteed to. So you can afford it, that's fine. I would again argue always keep in mind power and precision. But right now, the only categories I'm feeling comfortable about are row 1, cells 2 and 3. And for rows 2 and 3, I better be in the third column. But I would, if I started out here and this is what I brought to you, I would come back and say, expect V2. We're going to have to continue to refine this because this is too narrow. This is not focusing the landscape to an area where the clinician can really understand where they've got a good shot. Yes?
Quick question. With regard to the clinician that wants 4 tables, is it because they have 4 outcomes?
Yeah, but you got to understand.
But there's still only one primary outcome. Right?
There's one primary outcome in all these secondaries, but they're all 2 groups. They're all, every analysis is a 2-group analysis. Every outcome is a continuous outcome. So let me point out something to you. So I can tell you kind of ballparkish off of my head, if you tell me, I can come to you and say, if the 2 means are separated by 0.8 of a standard deviation, I can get 80% power with about 30 people. I know that based on experience. Okay, I just told you that. Okay, your first outcome has a standard deviation of 10. All right, then you better go look for an 8, right? 0.8 times 10 means you better set your means 8 units apart. Now I go to the next one. He's still stuck at 30 per group. Now he tells me the standard deviation is 15. 12. I will now do a calculation and show him 12. All I'm doing is playing 0.8 times the standard deviation. 0.8 times the standard deviation. There's no need for tables. Every table is built on the same solitary rule. So, all right. An adjustment here, what happens if I increase my sample size? If I increase my sample size, now I get up to 80% power. Always remember, increasing your sample size when you hold all other assumptions constant has to force your power up. Okay? Again, everything else in that calculation has stayed the same. The only thing I changed was now I said I'm going to go to 135 people in the study. If everything is held constant, increasing sample size will always increase your power. Because what are you doing? Bad form, but I'm going to back up some slides. Increasing the sample size simply warps or literally shoves that green curve to the right. You can imagine if you have an imagination, but sometimes I don't. I've tried to build slides where I click, 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 and as I change my sample size, this actually behaves like a wave. You see a wave forming and moving beyond the blue curve or the blue line. That's what the sample size is doing. It's distorting that green distribution as if it's a wave. Okay. Now, so that's it. It's again the same principles. Suppose you decided you want a more complicated design, possibly 2 treatments. Suppose treatment 1 is exercise and you have 3 types of water aerobics, standard aerobics, weight training. Suppose treatment 2 is randomized between 2 drugs. All of these things. Guess what? Nothing changes to the statistician. Nothing. All of this. All of these designs map to that. And that's what we're always thinking about. And what we need in this team science and this collaboration is for us to sit down and work on what defines this green curve. That's it. Okay. Again, you can get a really complicated design. Guess what, folks? It's still not going to change anything. To power the study, we're going to do a complex design where we've got two treatments, where we've got treatment 1 has 3 levels, treatment 2 has 2. Guess what? Now we're not now we're not guessing 3 means. We're guessing 6 means. And then I take those 6 means, I calculate out the variance, and one variance would be attributable to treatment 2, another variance to treatment 1, third variance is attributable to interactions. Is the gap between UB3 and UA3 equal to the gap between UB2 and UA2? Is that equal to that gap? So if you ever hear somebody say, what is a test of interaction? Test of interaction is testing within and saying, are the differences constant as you move across the table? Okay, that's the best way to think about interaction. All those tests would be there. All of those would have to be powered, but they all go back to the same principle. Draw the curves, shade the curves. That's power. With regard to proportion, again, proportions are the easiest thing for you. It's the easiest thing for statisticians. Just one bad news. They're very expensive with regard to sample size. Very expensive. Now, you can think about this. Again, when we do a chi-square, when we do a chi-square distribution, when we do a chi-square test, what we're really doing in the background, we're doing an ANOVA on proportions. Nobody teaches you that, but if you're doing a chi-squared test, what you've technically done is you've tried to do something similar to ANOVA on using proportions. That's all. So again, under the null, you would assume that in all 3 groups, the proportion is the same. Teaching example, we could assume 0.2, 0.2, 0.2. Guess what? There's no difference in the probability distributions across your 3 treatments. The null is true. There's only one probability distribution. They're all centered at 0.2. Under the alternative, we've got to start imagining different scenarios. We could do 0.2, 0.3, 0.4. You could do 0.2, 0.2, 0.4. That's harder because you set 2 of those proportions equal to each other. So that's going to be much harder for you to spot. You could do, Margot, if you really want to make me stay up at night, 0.20, 0.21, and 0.22. How to figure out to get that into a budget would be a very hard thing for me. But again, there's no difference. We're going to go back to these curves. If we wanted 80% power, we would need a total sample size of 306 or 102 per group. Okay? Again, I would do the exact same game as I've done before. If I'm going to submit this in a grant, I've got to give you this table. I would be very uncomfortable just handing you one power calculation. I would want to see the grid. I would lay out all my assumptions. Notice here, the variability here is smaller than the variability there. There are bigger gaps. 0.20, 0.30, 0.40 are bigger gaps than jumping 0.20, 0.25, 0.30. Hence, this should have really abysmal power. Guess what? It has bad power. You would not ever go there. But notice here, we're only closing in on 80% power when we get up to 300. Okay? Those are the types of things that we do. Again, question for you. Are any power calculations correct? When a statistician hands you a power calculation, what should be the first word in the paragraph? Assuming. Okay? Again, reason to work with methodology. Again, work with methodologists in the design, in any manuscript, that makes certain that the aims hypotheses, outcomes, analysis, and power all align. It's deadly to get to study section. And I've had to put this on the table. Great specific aims. How come your specific aims don't matter? Your analysis plan is completely inappropriate for what you have in your aims, and your power calculation doesn't even match your analysis plan. If they don't align, you got a problem. All right? All right, I'm in danger of going over, so I'm going to stop there and let y'all have 15 minutes. All right? You have a question? Closing questions.
So, the first part of the class, we talked about comparing the mean and standard deviation with normal distribution curve and calculate the power there. This time we are talking about ANOVA, compare the variance, analysis of the variance. Now, when do we need to use the ANOVA, and what's the difference between comparing normal distribution curves?
All right, so there's a great question right there. When do you go to ANOVA? ANOVA still assumes normality, just like we did at the very first thing. But if I go to 3 groups, anytime I go to more than 2 groups, I have got to get to ANOVA. If that is 3 groups, fine. If that's a complex situation where I've got 2 treatments, 2 levels on one and 3 on the other, well, that's technically 6 groups. That's ANOVA. Okay? So anytime I go beyond 2 groups, I'm in the world of ANOVA. Okay? All right, I think next week you have spring break, so I don't think I'll make you cut. I think I'll give you the week off.
No.
No spring break next week? We are meeting next week?
We're making up
We're making up? What are we making up?
the class that we missed in January. Snow day. The snow day that
We had a snow day? I can't remember a snow day.
It
was a snow day? Did it snow?
It was quote a snow day.
I don't remember a snow day.
It was
So what's next week's lecture?
It is clinical trial, phase 3 clinical trials and DSCP.
And then the week after that?
Is you again.
Oh, sorry guys, I'm back. I'll see y'all for rigor and reproducibility. That will be a...
I was in the Kaizen class, that was fun.
All right.
Rigor, reproducibility. I think they called it
R2T.
Yeah, that was good. He reminded me of my stats class from 1994. Professor Fuller at NYU, he taught the rejection region. And we used a book by Nancy.
Well, that's a catch. I mean, I tell the undergraduates and I tell the graduate students, they don't believe me. I finished my undergraduate degree, I finished my undergraduate in 91. Bachelor's in mathematics, 3 stats class, and 1 concept I was never taught. I was taught ANOVA. I was taught regression. I was taught 1 sample, 2 samples, testing proportions, you name it. The one thing I was never taught,
Rejection region. We had to draw these lines and share them. I kind of understand that it was funny, but before, I'll never forget.
I mean, I can understand they were in a different order, the same numbers in a different order, but there's.
Order does not matter in statistics.
Like,
But let me show you.
and then you
Okay.
say.
So we've got 30,
And then he was like, that's it. So I was like,
25,
fine.
25.
I don't know.
And then
I think I still have my.
This is the population variance, okay? This is the variance that we need to worry about.
I have her like
So 5.556.
It's 30.
The advanced field was almost. And when I got to my PC program, I forget how to say, I think he taught at UAE, or he was somewhere, I forget where he was. I was like, so I say that that was the only, to me, the friendliest statistical I've ever had.
So it's not even me.
You don't believe me still?
No, I mean, I think the way that I'm comprehending what you mean by the same, as long as they're the same number, but it doesn't have to be
The
like,
same pattern.
right. When I
Different?
say when I think pattern, I think just different combinations of 25, 25, and 30. Not that there can be two 25s or two 30s. I don't know how to explain what I'm
That would
trying
still
to
be
say.
the same number.
Right, but I comprehended it
So
differently.
that's okay, but did you understand here?
Now I understand. As long as
Okay,
it's
so
the
let me
same.
just point out something to you, okay? Let's do this. So let's measure from here.
Yeah, you do.
So let's go this way. Let's do this. What's the distance between 25 and the 25? Zero.
Yeah,
Right?
Howard now is based
What's
on
the next one?
None.
No, from 25 to 30.
but I overestimated.
And then, so we've got, so there's going to be,
25,
Oh,
25.
that's a good way
then
to
there's
say it.
25 to 25 is, so it's going to be another 5, right?
In my states.
So we got to do this guy to this guy, right?
25 to 25, 0.
Right? 25 to 30.
Is 5.
And then this 25 to that 30 is,
5.
there are your differences. Let's play this game. What's the difference between here and here? What's the difference between here and here?
I've never been to one of the bigger
first
sessions.
And what is the difference between, we got,
25 and 30, the
So
top
I
one,
need
5.
somebody to look at it.
Okay. Now I'm better. Thank you.
That's a good way. Are you going to talk about non-normally distributed statistics at all?
that's not parametrics. We can talk about it. If you want me to come back and do that, yes, I can.
I feel like a lot of the statistics are not non-normally.
So tell me about your data. Talk to me about it.
Retrospective data, but not the.
I love retrospective data. I want to teach a class on how to design very good retrospective studies.
I would definitely think the majority of residents would come and take that because that's what we have time to do. So I'm in radiation oncology and I did a dosimetry study looking at patients who had proton therapy versus photon therapy.
What's your outcome?
The dose delivered to various structures. So
You walking back to your office?
yes, I ran normal statistics and then I ran a test of normality and then I
And then the other day, so
well, I mean, that would be, I guess, the discussion that I think would be.
I know that.
You can bring like,
Because they're very robust.
It may be something that I should come to Monday session or Wednesday
Come
session
to
to talk about.
come to a Monday clinic.
Yeah.
Bring your data.
Okay, I will.
We'll
And
talk about it.
I haven't done the manuscript yet, but I do have a poster that I'll probably update before I present.
Thank you.
So I just come
Monday
by
at Lister
or
Hill.
Monday at Lister Hill. I will be there.